Hello and welcome to this presentation. So this presentation is on a localization framework for reasoning faults in LLM-based coding agents. So nowadays we are using large language models and we're also using large language models recently as agents. In this work, what we try to focus on is how we can figure out what was the thought process of the agent that led to generating a buggy code. There are existing works like Divine, Reaper Agent, and Reason Act Loop. So they all act in the form of reasoning and then acting, that is planning and executing. So this planning and execution we are calling hypothesis. And the problem that exists in the present setting is that when an agent fails, it rarely produces a simple syntax error. That is, as far as the observability part goes, it generates code that is logically incorrect due to the flawed internal plan. This is not otherwise available during the traditional conventional LLM without the agentic setting. Existing benchmarks like HumanEval, MBPP, and SWE bench, they measure the agent success rate. That's a binary, either it is passing or failing. They do not analyze why an agent is failing. So this is what we try to focus on in this work, and we target and we set on by first creating annotated dataset which links the agent's failure reasoning, that the hypothesis, parts of the hypothesis, to the resulting buggy code. So in some sense, we are trying to form a traceability between the hypothesis steps and the line numbers in the code. So this is what the prompt and the hypothesis, the corresponding hypothesis is going to look like. We see that the prompt has the main item of the prompt is highlighted in yellow, and the transformation of the agent thought process, the hypothesis, is driven by planning, then observation, then planning, executing, and these are interleaved. So the first contribution is the creation of a dataset because there is a lack of dataset. So we target the apps dataset, which is from Fort Parrot, targeting the coding competitions. It has 10,000 problems, 10,000 prompts. We decided to use a GPU server with a time limit of 3 to 4 days. And finally, we ended up solving 3072 problems, out of which 1622 were introductory level difficulty, 812 were interview level difficulty, and competition level difficulty was 638. So we can see that within that span, we ran all the three problems in parallel. That means the entire pipeline that you see on the right was executed for the different difficulty levels. So when we stopped, we saw that the harder problems were taking much time. Ended up having solved 3072 problems, that is 3072 out of the 10,000 in the original apps dataset, out of which we passed these problems to the agent under test, which is the Quen 7 billion code agent that is used as the agent. And the agentic hypothesis we extract using the LangGraph framework, which involves a lot of overhead. That also brings into account why we could generate only 3072 and finally to 615. So I will come to that number. So the Quen generates the code as well as the hypothesis. Then the generated code is fed to the test runner. The test cases that came up with the apps dataset code are validated. Then we have different failures, either syntax error, runtime error, or logical error. Those that passed, 609 out of them were discarded because they were not candidate for our analysis. So the failed cases without syntax error, that means only the 2450 were semantic error, flaw in the internal reasoning, due to which it generated semantically invalid code. And in all the settings, I would like to say that we used only one run. So there was no pass at k. The temperature was 0. So all the calls were made only once. For the commercial model, we use model B, GPT-4o. Although the model A also does reasoning to some extent, model B is a more powerful model which actually validates or tries to figure out what model A generated as faulty. So after this 2450 was fed directly to the model B, GPT-4o, we call this Oracle because this is where we are going to generate the ground truth due to. It tries to fix the code, also generates the localization information in terms of line numbers. After the fixed code is generated, we again return this code to the validator, which is again the test runner, and only those that pass, that means the code that are faulty generated by agent and that was fixed by the powerful agent, model B, and finally validated were included as 615 data points. And this is our subset of the analysis. The contribution to is having created this data set of 615. Final settlement was on 615 points. So what we do in the final localization pipeline is we have the model generated code that we use the Python trace utility with a dynamic analysis. So given the test failure log from the previous step and the code that was generated, we run the Python trace utility to extract the line numbers which were active during the execution of the faulty code. So that executed line numbers is and one part of information. The hypothesis logs that were created in the first pipeline, we feed it to an LLM, another LLM, which is again GPT-4o. This is a symmetric tracer agent. So the hypothesis log and the model a faulty code. From there, we try to figure out what steps of the hypothesis correspond to which lines of the code, and that gives us a trace map like this. So this trace map, the faulty code generated by model A, that is the agent under test, the test failure log, all these 5 pieces of information we give to a final debugger, which is GPT-4. It receives 5 inputs, and finally it generates the final prediction where it says what was the phase of the reasoning that led to most of the errors. So we had a 3-phase hierarchy where prompt understanding was the first part in the hypothesis, then the planning, then the execution. And we saw that out of the 615 analysis points, 73.82% was mostly for the execution phase. This means that generally the Coin 7B coder agent, which was our agent under test, that is the model A in this pipeline, it generally understands the problem. Also, the planning is also sufficiently good, just that it could not transform that understanding into the how to implement it in code. The second finding was that 3-level hierarchy was a coarse grained hierarchy. But if we try to do a much finer grained localization, when we bring it down to the line level, we saw that the results were not that good enough. So for that, we have a metric, root cause identification rate, that is the predicted buggy lines, and the buggy lines got inferred. Again, the ground truth is again due to the GPT-4o, that is the final debugger. And we saw that if we go for the strict RCI, that is exact match of line numbers, we saw a match of 4.07%, so it was very, very less. And in case of RCI lenient, if that is at least one line exact match, we saw that to 9.43% of match. The F1 score was very less because the 7 billion parameter model was also employed in this step, the final debugger. So model A itself from this pipeline was the coin. The final debugger is again the same model, just that to analyze whether a model can self-debug, self-repair its flawed reasoning process. The baseline is GPT-4o and the agent under test is the Quen 7B. So reasoning logs definitely contain valuable semantic information and which can help us in coarse grain for localization. So even knowing that which phase, whether the execution phase or the understanding phase, that also can help us target efforts to the different phases. Overall, our framework was able to successfully identify the category of errors in terms of the phase and the reasoning phase fault in 2/3 of the cases. So the artifacts are available in Zenodo, and thank you for attending this presentation.